No, everything is recorded. We're going to look at the example today for the heat exchanger. However, I would like to draw your attention to what do we have. We did set up ourselves with three equations at least, because when we have the heat exchanger, we're gonna have the heat exchange between the hot fluid and the cold fluid. From thermodynamics, if you take the control volume over the cold fluid, you're gonna get the first equation. Neglecting work, neglecting the uh, kinetic energy difference, and also the potential energy difference. This is the equation that you're gonna have for the first law of thermodynamics equation. The same way, if you take the control volume over the hot fluid, this is what we're gonna have. Okay, and the first equation and the second equation, they share the same Q, meaning that the heat transfer loss from the hot fluid gonna go to the cold fluid directly 100%, not losing it to the environment. And you get an option now for the third equation. You either use the log mean temperature difference equation, or you can use the effectiveness equation, either of them. Somebody found out that they use the both of the equation, meaning they're gonna end up with having four equations. That's fine, but for the sake of simplicity, I want to say we're gonna have the three equation, two of them from thermodynamics and another one from the heat transfer class. So if you set yourself up with kind of the understanding that I just talked about, we can go ahead and try to see if we can make use of what we learn. Okay, so let me start with this equation then, problem then. This problem setting you up with the counterflow concentric tube heat exchanger. It is used to cool the lubricant for large industrial gas turbine engine. The meaning the oil is hot. Cooling water is used, passing through the inner diameter of the tube, meaning that it is the concentric tube. You have a big tube in the outer ring, and you have the small tube in the center. Okay, you have the bigger tube over the smaller tube. In the smaller tube, you have the water, cooling water flowing in, and you have the diameter of the inside and diameter of the outside. You know the mass flow rate of the water, 0.2 kilogram per second. You know the flow rate of the oil, 0.1 kilogram per second. The oil and water entering the heat exchanger with the temperature of 100 degrees Celsius and 30 degrees Celsius for the oil and water respectively. And how long must the tube be made if the outer temperature of the oil is to be 60 degrees Celsius? Okay, so this is the what's so-called designing problem. you are asked to find the dimension of heat exchanger. So in order to find the properties of the fluid for the engine oil, because the inlet temperature is 100 and outlet is 60, so you can easily find the average temperature of the flow inside this heat exchanger. You just add 100 with the 60 and divide it by 2. You're gonna have the average temperature of hot fluid as this thing. Convert it into the Kelvin, 353 Kelvin, and use this temperature to find the Cp, mu, K from the table, okay? Which is available in the appendix of the book. Doesn't matter you use what kind of book, as long as it is the heat transfer book. The fluid property should be available in the appendix, but the number might be different from one book to the next. However, the water is kind of hard to specify the average temperature, because you know just only the inlet temperature of the water, 30 degrees Celsius, and you don't know the outlet temperature of the fluid. They don't even ask you about the exit temperature of the water at all. But I will show you at the end, we can find the temperature of the outlet water anyway. So in the beginning, we need to find the property of the water, because when water going in, it is the 30 degrees Celsius, all right. But when it's out, we don't know the temperature. So we kind of assume that the temperature inside over here should be larger than 30 degrees. So we kind of do something like trial and error, specifying the temperature of the water at the exit to be some value, which you know that the exit should be higher than the inlet, because it's the cooling water. At the beginning it's cool, but on the exit it's going to be warmer. So in this case, they suggest that we can assume the average temperature of the cold fluid to be 35. And then when we do the analysis, we have to check for the real exit temperature and check for the average temperature again, if it is the 35 degrees Celsius or not. If it's in the vicinity of 35, it's okay. But if it's not, you have to redo the iterations once again. Using this 35 Celsius, you can find Cp, mu, and K, and also the prime number of the water. So then how do we find the heat transfer? Remember, we have 3 equations. The heat transfer, the thermodynamics equation is just the Q equal to m dot Cp to the T. Right now, when you take a look at the data that we have the temperature of the inlet and the exit in the same time for the hot fluid. So we come to conclusion that we must start at the equation for the hot fluid first. THI is known, THO is known, it's given as, THI is the 100 degree, THO is 60, okay? M dot is given too. It is the 0.1 kilogram per second, which is plug it in. Cp, you already found it over here. Plug in, you're gonna have the Q equal to 8524 watt. So this is the Q that the hot fluid lost, and 100% of this is going to go to the cold fluid, which You already have another equation setting up for the cold fluid. Q equal to m dot C CPC T TCO minus TCI. Rearrange the equation again, the second equation, and this is what you have. Okay, so you're gonna get the TCO equal to 40.2. So this is the exit equation, exit temperature, and you have the inlet temperature specified by 30 degrees Celsius. But before doing this, you already assume that T bar for the cold fluid, the average temperature should be 35 degrees Celsius. So you just check it again. You add 40.2 that you found it recently with the inlet temperature and divided by 2, you're going to get something like 35.1. Luckily, you kind of assume it to be 35 degrees Celsius at the beginning. So right now you should be feeling okay that you started up with the first number of trial and error and you found it. Okay. So if it's not the 35, if it's not in the vicinity of 35 degrees Celsius, it's up to you if you're going to redo this part again. For example, if T bar C is over here is equal to 40, right? You take this 40 and add it up with the 30. I'm sorry, 40, and you should use this 40 to retry and error once again up until to the point where you got the new TCO and check for the T bar once again. And if you are satisfied with it, stop. You can proceed to the next one. Okay, so then now, because the fact that you're gonna use the third equation, this is a third equation, and you already know Q, this, and judging from the fact that the problems, even though the problem specifying you with the 3 temperature, hot fluid inlet, hot fluid exit, cold fluid inlet, but at the end, previously step, you found a TCO, the exit temperature of the cold fluid. So right now at this point, you know all 4 of the temperature, allowing you to specify calculate the delta lock mean temperature. Okay, so the delta lock mean temperature is specified by this. You need the THO, THI, you need the TCO, you need the TCI. You just substitute everything in, and you're gonna get the delta lock mean temperature. And you plug in over here, knowing that Q right here is equal to 8524. Okay, however, U over here is something that you kind of have to review everything you learn, how to find the UA. If I assume that if you look at the problem itself, heat going to be transferred from the hot oil to the cold oil, to the cold water. It got to pass through the tube. So at least there should be the thermal resistance of the hot fluid and the thermal resistance of the tube, the inner tube, and the thermal resistance of the convection inside. Once again, there must be at least 3 thermal resistance in order to find a UA. First of which, convection resistance on the outside, the thermal resistance of the pipe, and the thermal resistance of the convection inside. So you need 3 uh 3 thermal resistance to be combined as the UA. Let me find my pen first. I'll write it down for you. Here. You already know that U A equal to 1 over total, right? And total itself is 1 over HOAO. HO is the convective heat transfer outside the inner tube, plus natural log of d di1 di2 minus di1. I'm sorry, I should not minus sign. What did I do? It should be over di1 over 2 pi kl. Okay, when L is the length of the heat exchanger, plus 1 over HI AI. What is the DI1 and DI2 anyway? Because for real, the inner tube, it should have a thickness. Okay, and this is what I talk about. This is the I2, and this is DI1. Okay, so it is the inner radius of the inner tube, DI1. DI2 is the outer radius, outer diameter, I'm sorry, of the inner tube. Once again, DI1 is the inner diameter of the inner tube. DI2, outer diameter of the tube. Okay, but in this case, if you look at the problem itself, nothing here in the problem itself doesn't tell anything about the thickness of the inner tube at all. So it's safely to assume that when it is the thin tube, meaning that di2 approximately equal to di1 because it's thin. When it's thin, this one goes to 1. Natural log of 1 equal to 0. Okay? And also, di2 2 pi pi d2 multiplied by L should be approximately equal to pi di1 multiplied by L. This is the AO. This is the AI. Okay. So as a result from this, AO and AI must be close to each other and is equal to A. Okay. So when AO, AI uh, equal to each other, you're gonna have UA equal to 1 over HO multiplied by A plus 1 over HI multiplied by A, and A got canceled. In this case, at the end, this is what you're going to have. Oh, okay. So I wrote it down. U equal to 1 over HI plus 1 over HO, like so. Then, because I know that Reynolds number is equal to UM multiplied by D. Right now, D should be DI over nu. And also, I know that the M dot equal to rho A and UM. A is equal to pi DI squared over 4. Okay, so rearrange this equation. You can write the equation UM as a function of M and DI and substitute this into this. This is going to have. Okay, then M dot C is specifying, DI is specifying mu, you already found it. Over here, plug in, you're going to have the Reynolds number equal to 14,050. So this is the turbulent flow inside the inner tube. Okay, so you have to find the Reynolds number because Reynolds numbers is needed to find the HI. Why? The HI is HI for internal flow inside the circular tube. How about the HO? HO is for the flow outside the tube. Sorry, that's and it's not the external flow to either. Why? Because the flow outside the inner tube, but it's inside. It's inside the outer tube. Once again, let me repeat myself. HO is the convective heat transfer of the flow outside the inner tube. However, the flow itself is not the external flow. It's still the internal flow. It's the flow inside the annula. Because if you look at the cross section, the flow index. And sometimes you have to seek for the geometry, the external flow, the internal flow, inside some specific some specific geometry, and you have to browse it up. You have to look for it. Okay, so what I did, I tried to find you the HI first because the flow inside the pipe, the inner pipe, is turbulent flow, and you choose the relationship to find the Nusselt number for the flow inside the tube. This one looks good for you. It's used for the turbulent flow, and you just substitute your Reynolds number and Prandtl number, okay, for the fluid inside the tube, which is the water now, cooling water. So once you find the Nusselt number, you recognize that this Nusselt number is equal to HI multiplied by D over K. Rearrange this equation, you're going to have the HI. Okay. For the HO, like I kind of told you before, it is the internal flow, but it's not the flow inside the ordinary tube. It is the flow inside the annula. So I introduced to you this relationship of the flow inside the pipe. There are going to be two kind of the, I'm sorry, I introduced to you the flow inside the annular geometry. This is the annular geometry. Look at this. This is the surface. And you have a flow over here. Let's say, in the first case, if you are insulated, the tube is insulated outside. If there is a heat transfer from the hot surface, the shade surface like this, into your fluid on the white surface. Okay, and the Q double prime, the heat flux over here, is from the hot surface, the shaded surface, into the fluid, the white surface. The governing equation for the Newton's law of cooling governing this kind of flow is something like this. Just a reminding of what you have seen before. Q double prime I equal to HI multiplied by TSI minus TM. Okay, TM is the temperature of the flow inside over here. Okay, and then this is the HI. However, on the opposite side, if you are insulated on this surface, and this is a hot surface specified by TSO, if you have a heat transfer from here to there, this is what's so-called the HO in this setup. So two of this geometry, each of the NU Nusselt number is specified by this. You have to match what do you have in your problem, this case or that case, because the Nusselt number NUI and NUO is given for the flow where the ratio DI over DO is specified. Okay, your objective is now finding the HO over here. Okay, when you have a heat transfer going like that, right? Because I'm sorry. Going like that. In fact, because the fluid in this problem over here is hot, over here is cold. However, the heat going to be transferred from here to there, but interacting between the flow on this side and this surface. In spite of the fact that you're going to have a heat transfer over here, but this is your case. The heat transfer is not going to be starting from here to the fluid, no. Okay, but it's going to be exchanged between this surface and that surface, meaning that you're going to use this setup. Okay, so this setup, you have to find the NUI. This is your NUI. Okay, and you can find the HI. And the HI from this table is equal to HI from table is going to be your HO to be used for the U equal to 1 over HI plus 1 over HO. Okay. Let me repeat again for some of you who get kind of lost right now. I'm talking about the flow inside the annular region over here. Okay, from the previous slide, the flow going to be moving in the annular region, and it's hot, and it losing heat when it progress into the pipe, meaning that it losing heat like that. Okay, and then there is this table talking about this situation where you have the flow inside the white region, meaning that in this region. Okay, and they have a table for it, but this table is supposed to be used for two categories of the heat transfer. One category is the heat transfer interaction between the flow and this surface, whether in the out. What I'm specifying over here is the interaction between this one and the flow over here. Unlike this case, it is the interaction between this surface, the heat transfer from this surface, and the fluid. Okay, our case, heat transfer is not over here, it is over here. So it fell into this one. But in this table, they're specifying the HI, the heat transfer like this between the two subject, meaning the surface and the fluid, as HI. Okay, and this is what you want, except they use the opposite subscript. They call it in this table, table 8.2, they're specifying as the HI. But you use the HO in this case. But you have to match which one they're going to use. Not this one. It should be this one. Okay? Spend time with this one again and convince yourself that this is the way to go. I think 2 years ago, we'd have the final exam based on this. Okay? So in this case, you can see that for us, we have to change the NUI to NUO and HI to HO to match our case. It's the same physics. So, and you kind of find the DI over DO. This is DI and this is DO. Okay, and find the ratio. And after that, you read for the NUI. Okay, after you pick the NUI, you use this equation to be, for example, what I found. Okay. Oh, one more thing. It based everything here by the DH. And DH is specifying like this, which is the DO minus DI. So I take a liberty to find the Reynolds number of the flow inside the annulus. Base my D by the DH, which I already know it is the DI minus multiplied by DI. Okay, substitute my UM. I know that the UM rho UMA is equal to M dot of the hot. Okay, and this is UM, and this is pi dO over 2 minus di over 2 square over 4 equal to the M dot H. Rearrange this equation, and you get the DM UM, and plug UM over here. This is what you have. Okay, and then plugging in the number and Reynolds number equal to this. Okay, you can find your DI and DO equal to 0.56, and it's over here. So by using the interpolation, let me erase this. UDI and DO equal to this. Make the interpolation, your NUI is going to be the 5.63. Okay, so you use the NUI. And their HI is your HO. Rearrange this equation, finding the HO. You're gonna have the 38.8. So right now you go back to the equation that you started a few minutes ago. One U equal to 1 over hi plus 1 over ho. Substitute number in, you're gonna get your U. Okay, and you plug U over here and recognize that A is equal to, this is the surface of the heat transfer, is equal to pi d, pi di, this circle, multiplied by the length. This is the heat transfer surface. And rearrange this equation. Okay, this is what I meant. This is the pi di multiplied by L. Rearrange the equation for L and so forth. So basically, let me spell it out for you once again. It starts from the fact that you're going to have a Q equal to M dot C CBC TCO minus CCI. And you're going to have the Q, not the Q dot, equal to M dot H CPH THI minus THO. And the third one would be Q equal to delta T, I'm sorry, UA, and delta T lock mean temperature. You got yourself 3 equations. See? And you can see in this problem, all the unknown that you have to that you can find is one is T, TCO. You already saw for it. Check it out. Two previous slide, you already saw for TCO. Second of all, you solve for Q. And the third one, you solve for dA, or giving you the L. So see, 3 unknowns. You have yourself 3 equations. 3 unknowns. Other than that, the information should be provided by the problem itself, except this 3. Okay? When you have a system of 3 equations, you are allowed to have 3 unknowns. The cool thing about the final exam is that it's not open-end problem. They cannot give you 3 equations with 4 unknowns. They must give you 3 equations with 3 unknowns, meaning that they have to provide you enough information to make the calculation. And in this case, you use the log mean temperature because you know, in spite of the fact that you don't know all 4 temperatures. You know just only 3 specified by the problem. And why do I choose to use the LMTD? In spite of the fact that the LMTD itself need 4 temperature to find the delta T LMTD. That because I know all the M dot C, M dot H that I know. Okay. And I can find the heat transfer from the pair of the temperature that I know, from the M dot that I know. And then I use another equation to find another missing T. What I'm talking about is that this is specified by the problem. This is specified by the problem. This is specified by the problem, allowing me to find this, and knowing this, and given TCI is given to me like that, it's allowing me to find the TCO. There, I have 4 temperature right there. and then allow me to use the log-mean temperature difference. So now, some of the problem you cannot get the opportunity to use the log-mean temperature at all. This is the example that I'm talking about. Hot oil is to be cooled by water in 1 chill pass and 8 chill passes heat exchanger. This is 1 chill. 8 chill passes 1, 2, 3, 4, 5, 6, 7, 8. The tube thin wall. So once again, you already seen the tube which classified as the thin wall tube before in the previous example, and you know it's led to the how to find the overall heat transfer coefficient, or U. Remember, UA equal to the HOAO plus natural log of DO over DI over 2 pi K L plus 1 over HIAI. And because DI and DO is close to one another, natural log of 1 giving you 0. Ring the bell. Just take a look at the previous slide. It's gonna be used once again in this problem because they are already given, dictated by the information that's given to you by the problem itself. And the tube made with copper. Internal diameter it is the 1.4 centimeter. Okay, the length of each tube pass in the heat exchanger is 5 meter, and the overall heat transfer coefficient is the 310 watt per meter square Kelvin. Wow, you're lucky because this one is U. Overall heat transfer coefficient. Water flow through the tube with this rate, 0.2 kilogram per second, and the oil through the shell at the rate of the 0.3 kilogram per second. The water and the oil entered with the temperature of 20 degrees Celsius and 150 degrees Celsius. This is the temperature of the oil. So the oil is hot fluid. So this is the M dot H. And this is the M dot C going in. They are asking us to find the rate of heat transfer, meaning that you have to find Q and the outlet temperature of the water of the oil. Now, inlet temperature, 20 degree is given. Inlet temperature of the hot fluid is given. CP of water and the oil is given. So CPC is fine. CPH is given. Okay? This is for water. This is for the oil. No problem. Now, look at this thing. They are asking us to find Q, meaning Q is the unknown. Now, look at this. Nothing is given for the exit temperature, meaning that TCO and THO also the unknowns. And we already have 3 unknowns. And right now we have 3 equations. We already have 3 unknowns, meaning that everything else should be given. Now, we don't have the exit temperature. This is serious. Why? Because when you look at the equation of thermodynamic, Q equal to m dot C CPC multiplied by TCO minus TCI. That's one equation. Second equation is Q equal to m dot H CPH and THI minus THO. These two equations, you do not know the exit temperature, both of them, and you don't know the Q. See, unlike the previous example, you know three temperature, inlet and exit of the hot fluid. Another one, you know only the inlet. And the previous problem to make the situation kind of relax to you is they all given you the m dot C. Yeah, there they given you the m dot H. Knowing one m dot, knowing one inlet and the exit of that m dot, allowing you to find Q right here, in spite of the fact that m dot C and m dot S is given, but TCO and TSO are not given to you. You cannot find Q. Okay? If you introduce the third equation, meaning that it is the Q equal to UA and multiplied by the T log mean temperature. Okay? This is the unknown. One unknown is Q. Second unknown is TCO. Third unknown is THO. Okay? And this one need the temperature of all four, but you don't know two of them. You cannot find this one easily. Solving for the TCO and THO would be a mess because your unknown parameters is inside the log mean temperature. What do I mean by the log mean temperature? Take a look at this thing. The previous one. Here, see? THI, here TCO, here THO. You unknown, both of them are behind the natural log. Solving TCO and THO out of the log function is a mess. You need to try and error. Okay? In the problem that you have two of the temperature, another two you don't know, don't use the log mean temperature approach. Using the effectiveness approach. Okay? If you know the inlet temperature and the exit temperature of one fluid and another inlet or exit of another fluid, just only one of them. You don't have to know the second pair of the temperature. Just the first pair is fine. And the other fluid, at least one of them is known, either inlet or the exit temperature. It will allow you to find the fourth temperature anyway. Then you can use the log mean temperature. You can then you can use the log mean temperature to make your analysis. Once again, let me repeat myself. If the two temperature is known, another two unknown, don't use the log mean temperature approach. Using the effectiveness approach. If you know the temperature 4 of them, you are okay to use the log mean temperature approach. However, if you don't know all 4, but you know 3, plus you know the m dot, or you know both m dot, or you know the q, you still allowed to use the log mean temperature approach. This is the concept. It's not written in anywhere in the book. Okay, this is me giving you my experience, summarize things that you're gonna see in the homework and the exam. Okay, so in this problem, like I said, I will not suggest myself to use the log mean temperature approach. I'm going to use the effectiveness approach. So I find the CH and find the CC. Why do I need to do so? Because I need to find the epsilon, the effectiveness. By knowing that my epsilon is a function of NTU and CR. The NTU is UA over C min. CR is C min over C max. Okay, and C, big C over here, it is the m dot and multiplied by CP. There are 2 big C, one of which is a big CH, another one is a big CC. Big CH is equal to m dot H CPH. Big CC equal to m dot C CPC. We just substitute everything which are given by the problem itself. Okay, CP is already given over here, plug in here, and find it out if CH or CC is C min. If one of them is C min, the other would be C max. Right there, CH equal to this, CC equal to this, and this is C max, and this is C min. And at first you can find the CR, which is CR is a big C min over big C max. And then, because you have to find the A is the surface area, the heat transfer area between the two fluid, okay? And it's given by the problem itself. See, U is over here, but you need the A, okay? And you already got the C min. What is the A? AS is the surface area between the fluid in the pipe and the fluid in the shell. And you use the external surface area of the tube. So it is the pi dl. How? How is what? In this case, the length of each tube pass, meaning that this is the length of each tube pass. I specify this by L. Okay, so all the surface would be, this is the pipe, and it is the thin pipe, right? So the surface area would be circumference of the line, which is pi d right now, multiplied by L, and multiplied by N. N is the number of tube pass. You're going to get the AS. Okay, so A over here is AS. Finding the AS. 8, number of tube pass, multiplied by pi, the diameter of the tube inside, which is a thin wall tube, multiplied by the length of each pass. So you're gonna get yourself the AS. Then you find the NTU. UAS over C min equal to this. Okay. Now you got your CR. You got the NTU. So you're going to go to the plot where you have the one shell multiple tubes pass. Okay. And that plot is supposed to be used for the two chill passes and the multiple of two tube passes, meaning when you have four tube passes, six tube passes, or eight tube passes using that plot. Okay, finding the epsilon, and you will find from that plot that the epsilon is equal to 0.47. Okay, you substitute because you know that the relationship between epsilon and q is that q equal to epsilon multiplied by c min multiplied by uh, thi minus tci. This is the equation. Okay, why? Because you know that epsilon over here equal to actual q over q max, and q max over here is equal to c min multiplied by thi minus tho. In order to compute for Q, you need just only thi and tho, but you have to specify what is your C min, and you have to specify what is your epsilon, and you have to retrieve your epsilon by knowing the NTU, knowing the CR. This is what this is why we seek for the CR and NTU, because we know that if we know that after knowing this two, you can find the epsilon. And you plug in the epsilon over here, we write this equation, you can find Q. Okay, substitute on the number in, you're gonna get the Q equal to 83.1 kilowatts. And after that, see, this one is found. Other than that, being as or not, you can find the THO and TCO. Why? Because if you know Q from this one, you can find TCO. Providing that TCI is known, M.C is known, CPC is known. Okay, which already given in this problem, obviously. Q is already known. You can find the THO, providing that THI, M.H, CPS are given by this problem. And they did give you those. Okay. So rearrange this equation to find the THO, rearrange this equation again to find the CCO. Now you're gonna have the exit temperature of our two. Okay. Another problem, talking about not just the shell and tube heat exchanger. Let's talk about the cross flow heat exchanger. Okay, you got yourself the hot exhaust gas at 300 degrees Celsius going into the cross the flow heat exchanger, leaving at 100 degrees Celsius. Now, one temperature is specified as the inlet temperature. Exit temperature is specified. Okay. And then this gas is used to heat the water. Water flow rate is given to you as the 1 kilogram per second from the temperature of 35 to 120. So this one is THI. This one is M.C. This one is the TCI, and this one is TCO. The exhaust gas specific heat is approximately to be 1,000 Joule kilogram per Kelvin. So this is the CPH. And the overall heat transfer coefficient based on the gas side, it is the 100. This is a UH, meaning the hot side. Okay. So now you can see that we don't know Q, we don't know the THO, because we already know the THI. TCI and TCO is given. We don't know the THO. We don't know the Q. But the problem is does not ask you for the Q or even the THO. They are asking you to find the heat transfer surface area. See? AH. The surface area. And it just toy with you, giving the strange subscript that you don't recognize, that you haven't seen before, like DAH. Don't worry about it. However, you look at this problem and think about the concept that I told you. Right now, you have three temperature, inlet and the exit of the cold. Inlet for the hot. Actually, right there, you should recognize right away that you should be able to use the log mean temperature approach. You don't need the effective approach, okay? But they're asking you to use the NTU method, meaning using the effectiveness. They are forcing you to. So, no problem. The benefit of using the NTU effectiveness analysis is that it can engage with the case where when you have just only two temperature. You don't have three and you don't have four, you don't have two. Or even if you have 3 or 4 temperature, you still can use the NTU effectiveness method. Unlike the log mean temperature, at least you can have just 3 unknown, 3 temperature, 4 temperature. LMTD is fine. Let me repeat myself again. If you want to use the delta T log mean temperature approach, you need at least 3 temperature. 4 is the best. 3 is enough. The effectiveness or the NTU effectiveness approach you can use when you have 2 temperature. But if you have 3, if you have 4, okay, you can still use the NTU effectiveness. Okay? So, in order to use the NTU effectiveness, I use this equation first. Q equal to CH, TC, THI minus THO. Okay, rearrange this equation. CH equal to this. And I have the Q equal to CC multiplied by TCO minus TCI. This equation is important. Why? Because you know the temperature of the coal, 35 to 125. You know TCI, you know TCO. Okay? And then, because this is the same Q, you equate this equation with that equation and rearrange it again. So once I rearrange this thing, I will know that my m dot HCPH gonna be equal to big CC multiplied by this ratio. Okay. And okay. Not 3. We have all 4. I'm sorry about that here. This is 4 equations. This is THO. See? We do have 4 temperature right there. Both of the inlets, both of the exits. We are entitled to be able to use the log mean temperature approach. But the problem is ask you to use the NTU effectiveness instead. Fine. Okay. So you know the THO. What is this? What is it that you don't know? Oh, this is the CMH. You don't know the mass flow rate of the hot fluid instead. 3 of the unknown. However, using this equation, you can solve for the CH without knowing the M dot H. CH is equal to 1889. At this point, you'll be able to compare this one, your CH with your CC, and found out that CH, in fact, it is the big C min, and this is C max. Okay, so because of the fact that the epsilon equal to Q over Q max. Your Q max is equal to this. Finding the Q max first, substitute all kind of the number inside. And after that, from the cold side, Q equal to M dot C Cp multiplied by TCO minus TCI. M dot C is given. CPC is water. You just approximate it equal to this. Okay, you can find it from the appendix of the book, knowing the TCI is 35, the TCO is 125, okay? And you find the average of the temperature. 125 plus 35 is 160 divided by 2, it's 80. So you use the average temperature of 80, finding the CPC from the appendix. And then you can find Q. And after that, Q over Q max, you already got Q. You got the Q max. You substitute the Q max and Q over here, you're gonna get your epsilon, right? And then you know what is your C min and what is your C max is. You substitute them in, you're gonna get the 0.45, which is the CR. Okay, now because you know the fact that epsilon over here is a function of NTU and CR. Now you know the CR, you know the epsilon. You have to find the NTU. So in this case, I go to this plot, providing that I assume that it is the cross flow with the fluid on both sides unmixed, meaning it has its own channel to go through. Select this plot and read the plot, meaning that I know the epsilon is 0.75. So it's right here, 75. CR is approximately 0.45, 45. This is 0.5. So it's right here. And you leave it there. What you're gonna have is something like this. So approximately 2.1. Okay, you read it back. And knowing that the NTU is equal to UA over C min. Okay, so you rearrange this equation, solving for C min, AH, which is your unknown. Providing that you know the NTU, you know the US given by the problem, and you know the C min. Okay, so that's the example. I think I already sent the next assignment to you. I will check if I did at the end of this lecture. And now you're gonna get the chance to play with the other problem as the homework. Okay, so Let me take myself out from this one. And what I would like to do is starting the next chapter. Let me convert the file. Over here, what I need is the next one, which is this. Okay, and I have to send you guys the file. Let me do that. So wait for a minute. Okay. And then there, announcement. Okay, file already sent. So would you mind download that so that we can start for the next chapter? Okay, here we go. Now, what I would like to cover is the kind of introduction, continuity of the introduction of the radiation. We have heard about radiation before at the beginning of the course. I introduced it to you in the first week of this course, but let me do it again. Okay, radiation is the last mode of the heat transfer. It is the energy transport. It does not need the medium to transfer the heat, but it needs surfaces. It need the surface of the beginning point, meaning higher temperature surface. It need the ending point, ending surface, which should be at lower temperature. In between, no need for any medium. It can be vacuum, it can be space, contain nothing. Still, there will be any energy transfer from the hot surface to the cold surface. Okay? The concept is that if the surface or the object is at the temperature larger than 0 degree Kelvin, it will have the heat transfer in terms of radiation. And this kind of this kind of the radiation is called emission. Once again, let me repeat myself. The surface of the object with the temperature larger than 0 degree Kelvin, it will emit the energy out. That energy is basically radiation. But the radiation from the fact that the object on the surface having the temperature larger than 0 degree Kelvin, that kind of radiation called emission as the specific name. So this surface, it might have the temperature larger than the 0 degree Kelvin, specified as TS, larger than 0 degree Kelvin. It's emit energy out. Actually, it's emit energy in every direction, like so. Okay, but I kind of lazy enough, don't want to draw on the line. So instead of drawing a multiple lines, I use to sum it up to one single line. This is an emission out of the starting point or the starting surface. The ending point, basically the largest the ending point is everything else, because you focus yourself on the starting point, that your system losing energy out. That energy gonna go to the something else rather than the system. Something else. You can combine them all and call them with one name as the surrounding. The surrounding itself comprised of so many things, which for real, it can have different temperature. Okay? But if you can find the average temperature of all kinds of the surface, combining into the surrounding, see, the surrounding itself gonna have the average temperature. The surrounding itself acting like the enclosure, cover your system. And if the average temperature of the surrounding is not 0 degree Kelvin, it also emit the energy back. Okay, when the surrounding emit the energy back, some of them will reach to your system, but not all of them. It might not be all of them reaching to your system, because some of them might miss and back to the surrounding itself. Okay, and within this 2 weeks, I have to emphasize that this is the difference between convection, conduction, and radiation. Because in conduction and convection, when you have higher temperature surface, lower temperature side, heat always coming from the high temperature side to the lower temperature side. Doesn't matter. Conduction, convection, the same. Heat going from higher temperature to the lower temperature. Not in another way around. But in radiation, it's not like that. This is higher temperature. This is lower surrounding, lower temperature surrounding. Heat or energy will emit from here to there. And this surface gonna emit the energy back. There will be something called radiation exchange. Because the fact that the heat transfer from this one is hot, it will be radiating or emitting higher energy. This surface, on the other hand, it is at the lower average temperature, in spite of the fact that it emit energy back, but that energy gonna be lower than this energy. Coming back is lower than going. The net radiation would be setting this thing up minus this thing, going out minus coming in, going out larger than going in. So the net would be in this direction. Heat transfer will be from the hot surface to the low surface anyway, but that heat transfer is not the absolute heat, it's the net heat because it's the radiation exchange. That's the big difference between radiation and the other two, which are conduction and convection. Okay, so the average temperature of the surrounding is Tsar. Okay, the average temperature of the solid or the surface that you choose as a system is Ts. In this case, if Ts greater than Tsar, net radiation will be out. Okay, see, that's why I use the symbol Q radiation, comma, net, meaning that going out minus coming in. If the Q net is in this direction, meaning that this surface losing heat, losing energy. And you already seen from the beginning of the course, in convection and in conduction, what drives the heat is the temperature difference between if it's slab, you have a slab like that, you have T1 on this side, you have T2 on this side. If T1 is greater than T2, what driving the heat is the temperature difference between T1 minus T2. Okay? If you have a convection over the surface, this is Ts, this is T infinity. Okay? What driving the heat transfer? Q equal to HA delta T. Delta T is Ts minus T infinity. Okay? But you already seen what does drive the radiation is not the temperature difference, but it is the temperature to the fourth, the difference of temperature to the fourth. We will talk about this thing once again. And radiation itself, it is a surface. Okay? It is from one surface to the next surface. Emission from the one surface gonna go until it hit the another surface. You don't need the medium. Because why is that? Because energy leaving the surface as the emission. One, we call it emission, meaning that the energy will transform itself from energy into electromagnetic wave. Electromagnetic wave has one cool property, which is traveling without the medium. It's possible for them. Okay? Electromagnetic wave can travel without a medium, or when you have a medium, that still can travel too. When you have a medium in between two surfaces, this surface is hot, this surface is cold, okay? But both of its the temperature larger than zero. Emission from here, emission from there, up and down, and you got the radiation exchange. Radiation exchange itself, when you have the medium in between, you have to think of the temperature of the medium too. The medium itself, it has its own molecule. If those molecules have the temperature larger than 0 degree Kelvin, those medium, those molecules also emit the energy. That will make your problem complex. Okay? In this class, we recognize that there might be the medium in between two surfaces, but we can assume that the radiation or the emission from the medium, if you have it, is very small. Let me repeat myself again. You have a hot surface, you have a cold surface. You have the net radiation from hot surface to the cold surface. Okay? If you have medium over there, and that medium is not 0 degree Kelvin, for real, it's gonna have the its own emission too. But in this class, we assume zero emission from the medium. In other words, medium play no effect. Medium does not participate in our analysis. Okay, which is okay for the ordinary application. Then, well, example, this is the sun and this is the earth. Sun emit the energy. Its temperature is 5,000 degrees plus Kelvin. Emit the energy out. The energy travel from the sun to the earth. Okay, let me draw the precise sketch like that. Here, sun is the traveling to the earth. Some of it is going to travel to the earth. Some of it might miss the earth in another direction. Fine. Once it leaves the surface of the sun, it will convert itself from energy into the electromagnetic wave. Once it arrives to the earth, that electromagnetic wave gonna convert itself into energy. And it's gonna deposit the energy into the surface of the earth. Once it's travel through the space or even through the medium, it maintain its behavior. It maintain the property as a wave. Electromagnetic wave, the highlight would be wave, meaning that you can use this wave equation. Lambda equal to velocity of the wave over the frequency of the wave. Okay, so velocity of electromagnetic wave is the velocity of light. Okay, and the velocity of light equal to c0. C0 is the velocity of the light through the space or through vacuum, which is approximately 3 multiplied by 10 to the 8 meter per second. Okay? C over here is the velocity of the wave, electromagnetic wave, traveling to the medium. We have to know that medium first. And those kind of medium, it's going to have a property which we call N, the index of refraction. Okay? But if it's traveled, if we don't have a medium, N going to be equal to 1, meaning that the vacuum, the space, N equal to 1. Water, not 1. Okay? The water kind of have ability to slow the light down, but sometimes the difference might be so significant. Okay. When we talk about the electromagnetic wave, when wave travel, it can have so many kind of wave. Each of the wave will possess its own radiation. But all of the electromagnetic wave, when it travel through space or through one medium, it's going to have the same velocity. So the signature of wave would depend on frequency and wavelength. And the relationship between wavelength and the frequency gonna be according to this equation. If you know the lambda, you can tell the frequency. On the other way around, if you know the frequency, you can tell the wavelength. Providing that you can find C. How do you find C? C0 is just a constant, 3 multiplied by 10 to the 8. You have to know what n is, meaning you have to know what kind of medium that stay in between starting point to the ending point. Okay, when electromagnetic wave traveling. And it means if I tell you the lambda of my wave, you can tell me the frequency of that wave. On the other way around, if I tell you the frequency of that wave, you can tell me back, you can compute to me back for the lambda of that wave. So when you specify the lambda for the wave, it has its own class. For example, for the electromagnetic wave, which have lambda lower than 10 to the minus 4, we call it gamma ray. When lambda is low, meaning frequency is high. When frequency is high, meaning that it contains so many energy, so much energy. Okay? So gamma ray contain so much energy. Unlike the microwave. Microwave over here contain less energy than the gamma ray. Why? Because it contain more lambda. When you have more lambda, meaning that you have low frequency. Low frequency mean less energy. Okay? And better yet, our eyes sensitive to the particular range of wave. We can see things because the light one kind of radiation. For right now, I have my light bulb over here, okay, sending the radiation emission onto the object, and that object reflect the wave into my eyes, and my eyes have its own retina sensor, sensitive to some of the wavelength, not all of them, but some period of wavelength, and that make my eye can see whatever reflected, whatever reflects the wavelength, the electromagnetic wave. The wavelength that we can see is between here and there, 0.4 micrometer to 0.7 micrometer. This is the spectrum of the white light. Okay, so the white light itself is a combination between violet light, blue light, green light, yellow light, and red light. This is the rainbow colors. In fact, it has the 7 colored as you already know. Okay, so that's the portion of the light from the light source that you can see. During this the day, you will see things when you stand outside, seeing things from the reflection of the sunlight onto the object, reflected into your eyes. Okay, but in the darkest night, when you don't even have a moon, you don't have no light. How to say, no visible light reflected your eye, but it doesn't mean that it has no radiation at all. There will have some radiation from one object set reflecting to another object, to your eyes. But the problem is that the wavelength that reflected into your eye at that time is not in the visible range. This one is visible range. At that time and that night, nothing in the invisible range coming to your eyes at all. Some of the object is not at 0 degree Kelvin. It emits energy by itself. That radiation coming to your eye without reflection. But the type of energy traveling to your eye is not in the visible range. That's why you cannot see it. The thing that you cannot see it doesn't mean that it has 0 degree Kelvin. It might have some temperature. You cannot see it because it does not emit the energy in the invisible length, invisible wavelength, which your eye sensitive to. There are also another name, the electromagnetic wave, which has the wavelength less than 0.7, 0.4, up to the 10 to the minus 2. We call it ultraviolet X-ray from 10 to the minus 2 to 10.4. See, that's why you use the X-ray passing to your body, to the film. The film is sensitive. It's sensitive to the X-ray. Your eyes cannot. Okay, but you cannot expose your eye to the X-ray. You shouldn't for too long because it contains high energy. You cannot take X-ray so much often, every day, every hour. No. Okay, because it contains much energy. Exposing to the X-ray too much gonna cause you trouble. Okay, and the thermal radiation, though, coming out of the sun into the earth, it has the effect to the surface of the earth, which is the ending point from the for the light from the sun to the earth. This range about 10 to the minus 1 to 100 in terms of wavelength micrometer. It's called thermal radiation. This is the big portion of the sunlight traveling to the earth and increasing the energy of the subject. But the sunlight is not the only kind of the radiation source. My light bulb is one kind of energy source. Okay. Or the the radioactive material. That's another source, the kind of source of the radiation too. Doesn't have to be a sun. So then when you have the object, meaning you have 3D object, the surface of the object have its own temperature. Each part of the surface will emit the energy out. Okay? And then the element inside the object also possess the temperature, which when it's larger than 0 Kelvin, that particular element inside gonna emit energy too. In fact, every element inside the object will emit the energy. But in this class, to think of those is gonna be make the problem so complex to solve. We're gonna ignore, we're gonna assume that the element inside the object, the 3D object, does not involve itself with our analysis, meaning that we assume that the emission from the element inside is very small. The only part that we will engage is the emission or radiation from the surface. When you have the object, the 3D object, we have to view the system. We're gonna model it as the surface in spite of the fact that it's 3D. Okay? When you have the 3D, you will think of it as the surface. So, speaking of which, when you have a surface, okay, it can emit the energy. One point of the surface, every point of the surface, when you talk about each of them, it will emit energy in every direction. And it doesn't have to be equal in every direction. For this example, when you emit the energy out, it will be maximized when it's 90 degree. It minimized when it's 0 degree. Okay, so meaning that radiation is directional depending on angle. Okay, and then this will be the behavior of the surface in this shape. We use the length of the arrow as the intensity of radiation. This is much larger than this. Okay, so the length of the arrow is the quantity of the radiation. But this particular point of the surface will emit energy in this shape might be at some lambda, at lambda 1. But at lambda 2, it also emit energy. It might emit energy in this shape, but at lambda 2, meaning that right now, meaning that radiation does not depend on the direction only, but also depending on wavelength. Okay? When the radiation depending on wavelength, we call it spectral. When radiation depending on angle is called directional. Okay? And you can sum up all the energy in every direction and make a plot. You can see that at one wavelength, it emits this much. At another wavelength, it radiates this much. It can be varied. This is the evidence of radiation being spectral. Okay, and this is the example of this point on the surface of being directional. On Monday, we will talk about the how we find the total number. How we quantify all energy leaving the surface. in this direction, or try to find the summation of radiation in this direction to that direction, sum it up, neglecting on this side and that side, or sum it up from one wavelength to the next wavelength. Okay? Because for real, you want the total heat radiation or total emission. In spite of the fact that you know that heat, when it is emitted from surface, it can be vary in one direction to the next. It can be vary from one wavelength to the next. But the thing that you need most is how much in total, meaning when you sum it up in every direction, meaning when you sum it up in every wavelength, what kind of emission that you are looking for when the surface itself is at the temperature Ts, which is greater than 0 Kelvin. How much is it? Okay, we have talked about that on Monday. So, any question, guys, ladies, guys? Nothing. I will talk about this thing once again when we share the class together on Monday. Probably spill a few minutes preaching about this once again in Monday. So see you guys on Monday, and hopefully you already worked on the heat transfer project. Okay, you guys stay in the same group, or you're separate now? One separate. Type 2 if you stay as a group. Oh, two of you stay in the same group? Okay, fine. Either way. So work on it. Okay, great. So anything comes up, if you have a question regarding to the project, you can stop by my office or leaving me the chat on the Mango. I will be able to respond to you if you have problem. Other than that, if you don't have further any further questions, you are dismissed. So see you on Monday then. Have a good one. Till Monday.